the main topic of the talk is to think about ways in which we can link the fundamental properties of dark matter. Where by fundamental here, I really mean like the particle physics properties. What's its mass? What are its interactions? We start off with a particle physics Lagrangian for our dark matter model. How do we go from that to a prediction of what's going on in scales that are much, much larger, and in particular galactic scales? And what I hope to do over the course of the next hour is to give you some intuition for how to go from that sort of microphysics level up to that the big galactic physics level. And so this is all going to be in the context of comparing to cold dark matter, which we all know and love. It's been the standard in the field for decades. It has been spectacularly confirmed on the largest scales with our measurements of the cosmic microwave background and with large scale structure. Where we're at now as a community and as a field is thinking about how do we stress test this on much smaller scales. So as with any hypothesis that you put forward, you want to make sure that it holds up at all levels. We've done that with CDM on the large scales. And now the question is, how does it hold up when we go down to the small scale? So sizes of galaxies and also structures that are smaller than the sizes of galaxies. And there's a lot of confounding factors that come into play when we start zooming in on these scales. In particular, all the baryonic physics starts becoming important, and being able to distinguish effects from the baryonic physics and the dark matter physics is really the tricky part in this game. But that's kind of what we need to be focusing on if we really are going to make sure that CDM holds on all of these scales. Now, why is this an opportune time to be delving into this to study? And I think there's sort of three key things that are coming together all at this point in time. The first is there's been really a resurgence in model building going on in the particle physics community, a rethinking of the kinds of models for dark matter that are viable. And while there were many decades spent thinking about dark matter models in this mass range here, these days, with a lot of this additional model building that's been going on, we really are starting to think about dark matter scenarios that fall over much larger mass range. And I'll talk about this in quite some detail later on in the talk. That's coming at the same time as tremendous improvements with, on the technological side, sort of running numerical simulations of galaxies, right? Showing here, this is a mock data, mock Gaia data of a Milky Way galaxy from FIRE, from Robin Sanderson. And it's just spectacular when you look at that, right? You're forming a disk, you're getting a lot of the kinds of structures that you'd expect to see from galaxies that are the size of our own. So this, there's really, just the improvements that have been made on this front are really kind of setting us up for starting to integrate these dark matter models into these simulations. And then lastly is just the wealth of data that's coming online, especially on the astrophysical side. I'm showing here an image from Gaia, but that's what we have now, just over the next decade, right? With Rubin, Roman, JWST, Euclid, I'm missing. There's so many. Anyways, tons of data coming our way that are really going to be probing these structures. And so we want to be able to understand how we can interpret this data in terms of the particle physics models. Okay, so the outline of the talk, I want to start by just kind of reviewing how we think about galaxies in a cold dark matter framework. And this may be a review for some, but I kind of want to set up some of the terminology because I'm going to use this as a contrasting point as we then move on later in the talk. Once we start talking about dark sectors, which is sort of a broader class of dark matter models, I then want to kind of revisit this picture that we're going to paint in the beginning and think about how these sort of galactic probes are going to be changing in the context of adding additional dark matter interactions into the picture. All right, well, let's start off with CDM, our good old friend. So in the cold dark matter framework, when we think about galaxy evolution, we start off in the very early universe with small density fluctuations that grow into halos. Those halos end up capturing gas. Those are the sort of the beginnings of our galaxies. We then grow sort of bottom up with these galaxies combining through hierarchical structure formation, growing into larger systems, capturing more gas, forming stars. You start getting disks in these later on, to the kind of galaxies, the spiral galaxies that we see today. The assumption of cold, when we talk about cold dark matter, is really important at this stage here. When we say cold, what we're essentially saying is that the dark matter in these initial halos have a very small free streaming length, so they're caught in these halos, they don't free stream out, which means that these structures survive and then continue on in this process. If we change that assumption, so if we make the dark matter hotter, such that its mean free path is longer, the dark matter here will free stream out. These galaxies won't, these dark matter halos won't form. At least the smaller ones won't form, they'll get washed out. And so then that ends up wiping out some of the structure as you move further along in this evolution. So one way to capture that is to talk about essentially just doing statistics on the numbers of halos that we have of a given mass, which is referred to as a halo mass function or subhalo mass function. I'm showing an example here. This is halo mass on the x-axis, and the y-axis is just the number of halos in each given mass bin. And in the cold dark matter case, because we are able to preserve structure to very small scales, the prediction is that follows this black line. So just increases all the way down to very small scales. You end up going down to about Earth scale masses, halos down to Earth scale masses in cold dark matter. That's a very sharp prediction of the theory. And any deviation from that would be a really strong indication that it's not cold, that the dark matter is doing something else. And just as a point of comparison here, these are a few other models. I'm not going to go into detail in them at this stage of the talk, but just to kind of show that as you start varying the dark matter physics, you end up getting deviations from that cold dark matter prediction. A lot of those deviations occur roughly at halo scales of 10 to the 6, so much, much larger than the turnoff that you get from cold dark matter. And so if you're able to probe structures down to this scale and you see a deviation from the CDM expectation, that would be a very strong test of the cold dark matter hypothesis. To give you a sense where we are observationally, the red stars here are the classical Milky Way satellites. The blue dots are constraints coming from looking at perturbations of stellar streams, and the purple are coming from strong lensing. And the thinking is with the data that's upcoming, both from the stream data and also the strong lensing data, that we're going to be able to get much stronger constraints going down to about 10 to the 6, 10 to the 7, which is precisely that kind of really exciting regime where we can start testing and looking for deviations from CDM. Another interesting feature of the cold dark matter hypothesis is that in a dark matter only framework, so before we add baryons to the theory, no matter which scale you look at in each of these halos, you typically end up getting the same kind of density profile for the halo, which is kind of interesting. It's sort of self-similar on all of the scales. That profile is referred to as Navarro-Frank-White profile, or NFW. The key feature for our purposes is that it's essentially cuspy. And by cuspy, what I mean is if you plot the density of any one of these halos as a function of radius, the profile kind of goes up and it's very sharply peaked near the center. For most of the halos, so like this NFW type model, that means it goes up here as about 1 over R, is how it increases. Now, the story changes when you add baryons to your theory. Baryons give you feedback, you get supernova explosions, energy injection from AGN at the center of these galaxies. When you inject energy in the center of the galaxy, it ends up redistributing the dark matter that's there and can push it out. And so one consequence of this is that you end up coring the halo. So you move the dark matter out and you have less near the center. So a core in this case would be just essentially flat in that density profile. Now, when you get cusps and when you get cores depends on which system you're looking at. So this is a cartoon diagram trying to kind of very roughly summarizing results from a variety of simulations. It's showing the inner slope of the density profile as a function of galaxy mass going from ultra-faint dwarfs all the way up to Milky Way mass systems. So a chord, if you're chord, you live up here. If you're cuspy, you're further down here. And what you can see is that baryonic feedback doesn't just core everything. It primarily cores these bright dwarfs. And the reason for that is actually very intuitive. When you're down here, you really don't have that many baryons in your system, so you don't actually have that much feedback. And so it's pretty much dark matter dominated. It just reverts back to look like the NFW. When you're in this regime here, so Milky Way mass scales, you do have a lot more gas and baryons there. Feedback is going to be happening, but you have a ton of dark matter that's already there. And so you just don't have enough energy to redistribute all of it. So you just remain cuspy. And it's in this sweet spot here where the feedback is strong enough to effectively move around the dark matter that's inside your dwarf galaxy. And finally, kind of the last ingredient here is just thinking about what happens to one of these dwarf galaxies when it's captured by some host system. So here I'm assuming some Milky Way-like host. It will be cuspy density profile. The dwarf galaxy that's falling in can be chord or cuspy, depending on the degree of the feedback effects. The orbital path that dwarf galaxy is going to take is just given by that equation of motion, which I've written up there. So it's going to depend on the host potential, as well as the dynamical friction that's felt by the satellite, or kind of a gravitational drag force. And as it evolves along that orbit, it will lose mass due to tidal forces. The tidal forces will primarily be stripping away material in the outskirts of the galaxy, where the forces are strongest. And I put this up here just because we're going to be coming back to this. This is essentially the rate of mass loss from these tidal forces. And it depends on the total mass outside of the tidal radius. So the degree to which you end up losing mass will be dependent on the density profile of your dwarf galaxy. So if you change anything in that, so if you make it chord or cuspy, you will end up changing how much mass is lost by that satellite as it falls in. So taking all of those ingredients and putting them together, and then putting on your dark matter goggles so you can see the universe, just the dark matter distribution in the universe, you see something like this. So this is actually from a dark matter only CDM simulation by Mark Vogelsberger. This is a Milky Way sized halo. So here's the center. All the bright spots are all the dark matter subhalos. You see that there's a ton of structure. They go down to really small scales. Again, that's sort of the key prediction from CDM. The larger ones of these here are going to be actually contain stars and gas. So those will be like visible dwarf galaxies. But then you'll also have a bunch of less massive ones that are going to be completely dark that are flying around. Okay, so I kind of wanted to gather together a lot of the sort of key ideas from the CDM picture and start building a list of what aspects of galactic evolution are tied to our assumption of cold dark matter. Because for the rest of the talk, what we're going to end up doing is start moving away from CDM and adding to this list other items that are going to be affected when we start changing the particle physics. So the things we've mentioned so far is cold dark matter gives us a minimum halo mass. It affects the internal density distribution of both the host galaxy and any satellites. We know that there's tidal disruption that's happening, so mass loss through that mechanism, and also drag forces that are felt by the satellite during the orbit. In this particular case, it's going to be dynamical friction. So keep this in the back of your mind. We're going to be coming back to this list a few more times over the course of the talk. All right, so that's the setup. Now we're going to start moving away from CDM and introducing this sort of broader class of dark matter models that's referred to as dark sectors. To put these models in context, I kind of want to start going into a little bit more of the particle physics, about how we think about a cold dark matter model. So typically, sort of the model that everybody thinks about when they think CDM is WIMPs, which stands for weakly interacting massive particles. In this context, what we do is we have the standard model of particle physics, which is indicated here. Those are all the particles and that we know of. And then we add to it one additional dark matter particle. And we say that it's allowed to interact with any of the standard model particles through any of the forces that we already know about, which if we want the dark matter to be weakly interacting, pretty much resigns us to the weak force, the theory. And that's pretty much the basics behind WIMPs. The reason why this has been such a popular model and is really because it works cosmologically. And so oftentimes people refer to it as the WIMP miracle. The miracle comes from the fact that these simple assumptions end up giving you an abundance for your dark matter that matches the abundance of dark matter that we get from the CMB. So the WIMP miracle is as follows. So you assume in the very early universe, the dark matter is in equilibrium with the standard model. So you have these interactions where two dark matter particles annihilate into the standard model, and then the back reaction occurs as well. This continues. The universe is expanding at the same time. And at a certain point, the universe will have expanded enough that the two dark matter particles will no longer be able to find each other to annihilate. And so at that point in time, you shut off one direction of this. You fall out of equilibrium, and the abundance of dark matter at that point in time is just going to be the same abundance of dark matter that we see today. And that, if you work this all out, comes out to the following. This is the dark matter abundance, and it scales in this way with the dark matter mass and its interaction strength with the standard model. So if you assume that this is a weak interaction strength, and you assume that the dark matter is also weak scale, so roughly 100 GeV, TeV or so, then this works out to give you an abundance of roughly 0.1. And so that's what people refer to as the WIMP miracle. You just assume here that weak scale parameters and it all works out. Now, the question is this really a miracle? How much of a miracle is it? You may just sort of stare at this and say, well, okay, if I change these ratios a bit, this will still get to work and I get different masses, right? And the answer is yes. Over the last decade or so, there's really just been a tremendous amount of thought in the particle community about interesting ways in which you can do this and sort of move away from this WIMP paradigm. And I'll show you one that I like pretty much for its simplicity. This is just, I mean, there's so many. I could have given a whole talk just on that. But this model is nice because it's really simple and just kind of shows you how one small change is enough to give you rather dramatic consequences observationally, but still end up giving you the right relic abundance. So this particular scenario is referred to as forbidden dark matter. What we say is now we have a case where we add one additional new particle to the model, which I'm calling gamma D. And I just assume gamma D is some other dark matter. It's a little heavier than my chi. So I can have now the chi annihilate into these two heavier states. And then the story kind of proceeds from there. It's the same thing where they're in equilibrium in the early universe, they fall out of equilibrium. The resulting relic abundance is given here. And the key change from what we had on the previous slide comes in from this exponential factor that shows up. So now what I can do is, for example, keep this interaction strength fixed at a weak scale interaction, reduce the dark matter mass. That gets compensated by this additional exponential factor there, and I can still end up recovering the correct relic abundance today. So a small switch in the set of assumptions about how the dark matter is interacting in the early universe, and I'm still able to get the correct relic abundance. But I also get more in the sense that now that I've added this additional particle, I end up getting interactions like this, which essentially means that the dark matter can interact with itself. So I wanted to show this as an illustration of the fact that when you start thinking about other kinds of dark matter scenarios, you can still get the correct relic abundance, but you end up introducing new physics that ends up resulting in other kinds of interactions which you can observe with, like you can actually see on galactic scales. So putting this kind of back into our cartoon picture, our WIMP model sort of fell in this category. When we want to think more broadly about these other kinds of models referred to as dark sectors, what we do is we put all of the dark matter physics in its own separate sector here. We separate it out from the standard model. in this separate sector, I can have one dark matter particle or more. I'm not sort of limited by that. I can also add new forces that are indicated here by these green boxes. And so I can have a lot of interesting dynamics going on just in this sector alone. Now, in the simplest version of this, all of this interesting dark matter dynamics can be happening separate from the standard model. And the only way the two can communicate with each other is through gravity. But I can also consider other scenarios where there are new particles that mediate these interactions, such that you can have your dark matter interact with the standard model particles. So coming back to our really simple example here, in this case, for this forbidden dark matter, I'd have a chi, that's one of these yellow boxes. I'd add this gamma D, that's one of these green boxes. And that would be my dark sector. It would consist of this chi and this gamma D. I can do more complicated things where the gamma D is actually the mediator. That's also fine, but I won't get into that. So you might be looking at this and wondering, okay, gosh, now we've just made everything possible. So now we just have this, it's anything goes. And that's actually not the case. There are a lot of sort of theory restrictions that end up limiting us to certain classes of scenarios to consider in this context. So very briefly, one constraint comes from just the renormalizability of the theory. That actually ends up limiting the number of mediators that are allowed here. So we break those down into 4 classes of possibilities. The other important constraints comes from the early universe cosmology. You can add all of this additional stuff, but if you break the CMB or large scale structure, that's obviously bad. You also need to make sure that you can reproduce the dark matter abundance today. So these 2 constraints are actually quite strong, and it means you can't just write down whatever you want. Any new model has to survive these kinds of tests in order to be viable. The end result of these kinds of dark sector scenarios is that it opens up a much wider range of dark matter masses that we can consider. So to put this in perspective, WIMPs sort of live in this mass range here. Dark sectors are a much broader category, and depending on the kind of scenario you think about, you can fall anywhere in this mass range. If you're below an electron volt, your number densities are so high that the dark matter actually acts like a wave, like a coherent wave. So when we talk about like wave-like dark matter, you might have heard this as fuzzy or QCD axions. We're essentially talking about this class of dark matter here, where it's acting like a wave, like a coherent wave. Above this mass range, the particle picture is better. You don't have such high number densities for the dark matter. And so we think of things in this mass range more like particle scattering. There's so much to say about all of this. For the rest of the talk, I'm going to be focusing on 2 examples from this regime here, but one could give a whole separate talk just on this, also for implications on galactic scales. Okay, so with that set up, I now want to delve into 2 specific concrete examples to kind of work through how changing the dark matter physics ends up impacting galactic probes. And the 2 examples I'm going to focus on first is just starting off with dark matter that can interact with itself, but does so elastically. And the last example is where those interactions continue to occur, but where energy is allowed to be dissipated from them. So it's an inelastic self-interaction, using the word dissipative instead of inelastic. Okay, so the self-interacting picture was actually first proposed in this paper by Spergel and Steinhardt. And the basic idea underpinning that paper is very simple in the sense that you can ask, well, if I allow the dark matter to interact with itself, and I want it to be relevant on galactic scales, then what kinds of interaction cross-sections do I need? And so you can say, okay, if I look in the center part of a galaxy, and I want there to at least be one dark matter that scatters off another dark matter particle over the age of the universe, that will happen if I have an interaction cross-section that's about 1 centimeter squared per gram. So that was kind of the target that they set in that paper. Now, that kind of cross-section is actually very typical for dark sectors. It shows up in a lot of different kinds of models ones with light mediators. So there's certainly been a revival over the last few years in thinking about these scenarios because they are coming out to be very generic in this context. So for the purpose of example, the SIDM model that I'm going to consider looks like this. In this case, I have two dark matter come in, they interact via this light mediator particle here, and they just scatter off. And in the non-relativistic limit, this is essentially just a Yukawa potential. So you can think of it that way. The key prediction of this is that the interaction cross-section for the dark matter is going to be velocity dependent. So I've written it out here in full. The scattering, so the cross-section for scattering has this velocity that shows up in the denominator there. There are two free parameters that fold in here. So there's the sigma naught, which depends on the fundamental parameters in the theory in this way. And there's this omega, which depends on the, it's a velocity scale, and it depends on the fundamental parameters in that way there. And so whether or not the self-interactions are going to be relevant for the system that you're interested in is going to depend on what the sigma naught and the omega are. So for example, here I'm plotting cross-section as a function of velocity, and just highlighting where different size systems fall. So dwarfs are kind of here, Milky Way velocities here, clusters are up here. So if my dark matter model has a scattering cross-section that looks like this green curve, then that's telling me that I expect to see self-interactions in dwarf galaxies, in Milky Way systems, and also in clusters. I can change my dark matter model, changing these fundamental parameters here. That would give me a different velocity scale here, such that the cross-section falls off like the blue curve. If I do that, then that would tell me that for that model, self-interactions will be relevant in dwarfs, but will do absolutely nothing to a Milky Way galaxy or to a cluster. So you can see very clearly here how you essentially tune whether or not the self-interactions are going to be relevant in your system of choice by appropriate selection of those fundamental parameters. So once we allow for these self-interactions to occur, the actual physics of what's going on inside a dark matter halo becomes really interesting. It's much more interesting than the cold dark matter case. And it is multi-stages of the evolution of what will happen in the halo. Starts off with the formation of a core. So you start, when self-interactions are allowed, you can have heat that gets transferred in different regions of your halo. And so initially, the heat flow goes towards the center of the halo. So you start heating things up in the middle. That ends up moving the dark matter out a bit. And so you end up coring your galaxy in this region. The degree to which you can core, though, depends on how many baryons are in your system, because the baryons are going to be deepening the potential well here. So if you're in a baryon-dominated galaxy, your ability to core will be suppressed. The self-interactions will want to core, but they won't be able to move out. The dark matter won't be able to move out because the gravitational potential is going to still pull them back in. If you're in a dark matter dominated system, that doesn't end up happening. And so the dark matter will easily end up forming that core. So this effect has been observed in simulations. So this is one result where you can see density as a function of radius. This is a system that's dark matter only with self-interactions, and you get this core that forms. And then if you add a disk to that same galaxy, the resulting density distribution is the purple line. So it's no longer cored in that case. The nice consequence of this is that it ends up giving the model enough flexibility to be able to explain diversity of galaxies. So this is kind of a lovely feature of this. So by diversity of galaxies, what I mean is the observation of rotation curves in systems of essentially the same size. When you look at them, so this is circular velocity as a function of radius, the steepness of the rise in the rotation curve varies quite a bit over the different galaxies that are sampled. So even though they all end up at the same asymptotic value, how fast they get there changes. And why this occurs is sort of an open question, like why you end up seeing that diversity in galaxies. The SIDM explanation gives you a mechanism to be able to do this. These galaxies here tend to have high surface brightness, so they will be the baryon-dominated ones. So that means that you won't form the core. So your halos will be cuspier, and the rotation curve will rise faster. These galaxies, the red ones, are low surface brightness galaxies. So you have fewer baryons, which allows your halo to core, and so the rise will be slower. So you end up getting, in the SIDM framework, this flexibility to be able to explain the diversity problem. However, as we discussed earlier, even in cold dark matter, you can form cores, right, from feedback. And the degree to which you end up coring also ends up having this kind of relationship there as well. So you can ask, well, is there a preference if we look at collections of rotation curves from nearby galaxies? Is there a preference for SIDM versus this cold dark matter? This was a project actually that I gave, that was led by an undergrad, Aiden Zentner, as well as Siddharth Dantavate. I didn't have his photo, and postdoc Oren, who's in the back. This project actually started right at the beginning of COVID because Aiden has lost his summer research opportunity. So he just came to my office and was like, is there anything I can do? Gave him this, and hey, turned into a paper, which is pretty awesome. So what Aiden did was he looked at the rotation curves from 90 galaxies and fit them to cold dark matter models with feedback, without feedback, and also SIDM, and did a full Bayesian comparison to ask, is there a model preference for one versus the other? And what he found was that there was no model preference. So in some sense, the data, either one looked like it was a good enough fit. And you can sort of see that from these 3 example galaxies here. The CDM with feedback models are shown in red, the SIDM are in green, the data is in black. And in each of these cases, like there really isn't a strong, you can sort of see they both do equally as well in fitting. So, and the spark galaxies are some of the largest rotation curve data sets that we have to date. So at least with this set, it doesn't look like it's enough to separate out these 2 models, although as we continue to getting more rotation curve data, it might do better. That doesn't mean that we don't have any constraints on SIDM. So we have constraints coming from galaxy clusters and also Milky Way dwarfs. I'm going to summarize those constraints on this parameter space, which is the SIDM cross-section here and the velocity scale. So just to remind you, this falls out of our theory. The velocity scale is this parameter down here, and then the cross-section is the sigma naught up here. And the limit of velocity-independent cross-sections falls when you go up here, where that omega is really large. So what regions of this parameter space survive? This region up here is excluded from the fact that you don't end up observing cores in galaxy clusters. So groups and clusters, you're probing velocity scales on the order of 10 to the 3. You don't end up seeing in these relaxed clusters significant coring, and so that excludes this regime up here. So that's a very strong constraint. As Oren recently pointed out in one of his papers, if you look at some of the dwarf galaxies in the Milky Way that are very centrally concentrated, Draco is a really nice example of this, that can also be inconsistent with the core. And so those constraints end up ruling out this region here that's shown in blue. So what ends up surviving? The white regions. This white slice down here is essentially a region of very little self-interaction. So this is where this is essentially just cold dark matter. The other region that survives is this one here, where self-interactions are definitely at play. And actually really interesting stuff starts happening up here, which I want to describe in the next couple of slides. Up until this point, the only thing we've used is the fact that SIDM tends to form cores or may form cores in galaxies. But that's not the end of the picture. That stage where it forms core is actually not an equilibrium state. It's temporary, so to speak. after a certain point in time, the heat flow will reverse direction and flow back out. And what that ends up causing is the core to end up shrinking in size. And it shrinks down to a point where it completely collapses, and you end up getting this very high density region in the center. For field galaxies that are just isolated, the time scale for this process is very long. So it's longer than the age of the universe. So this process isn't relevant for those systems. However, for dwarf galaxies that are in the process of being tidally disrupted because they're falling into another galaxy, that tidal stripping actually accelerates this. So for dwarf galaxies that are in this process of being tidally disrupted, you do actually have a chance of forming these cores. Core collapse and getting these peaks in the center of the dwarf. The other important places where the self-interactions come at play when you think about galaxy mergers is in the mass loss that occurs for the dwarf galaxy as it falls in. So earlier when we were thinking about CDM, we talked about tidal stripping and how that removes dark matter from the outskirts of the galaxy as it falls in. Well, self-interactions are going to change the density of that dwarf galaxy. It may core it. If you have gravothermal collapse, it may actually cause it to have a little really concentrated. That's going to end up changing how much mass is lost through this tidal stripping process. So that's one key way in which SIDM ends up affecting mass loss. The other way is totally new and very different. We just don't have this in CDM. This occurs from the fact that the dark matter in the dwarf galaxy can interact with the dark matter in the halo. So, because now we're allowing those interactions. So as the subhalo falls in, you end up getting the scattering between the dwarf and the background halo, which can kick out dark matter particles from the dwarf. So that's just ram pressure evaporation. The net effect is different from the tidal stripping in that it actually ends up removing dark matter from the entire region of the halo, not just the outskirts. And another effect that can come from this is you can get a change in the momentum to the dwarf galaxy from the scattering. And that's called ram pressure deceleration. It tends to be kind of only relevant for very, very large cross sections. So I'm not really going to talk about it much more, but I just wanted to kind of throw that in there because it's another effect that comes into play. So tying this back to where we stand today, I was telling you that this is the region that sort of remains allowed. What does this tell us? Well, it tells us that if we have self-interacting dark matter, you need to have velocity-dependent interactions. It needs to live in this space, and this is precisely where velocity dependence becomes important. So we shouldn't really be talking about velocity-independent scattering dark matter. We know we would have to be this kind of model. The second thing that's key is that when you live in this region here, that actually is a regime where the gravothermal collapse can start occurring. Whether and how strong it is kind of a complicated question and one that we're kind of continuing to investigate now. But suffice to say that systems here might actually have gravothermal collapse occurring, and that's something that we're going to want to think about in the context of, let's say, dwarfs in our Milky Way. Maybe some of them are in the process of undergoing gravothermal collapse, maybe some are not. The last thing I just wanted to add was in this region here, that's also where tidal mass loss for the dwarf galaxies will be different and will be accelerated relative to cold dark matter. So taken together, the region of parameter space that's surviving here is one where you would actually expect if SIDM is the correct model, you would expect different densities for your satellite galaxies, as well as an impact on the overall population. The orbits should change because their masses are going to change. Okay, so to tie this into the list that we started building earlier, all of the effects that we talked about in cold dark matter are still at play for SIDM, but now we're going to be adding a few more. So now we have ram pressure deceleration, which is an additional drag force felt by the satellite. And we have ram pressure evaporation, which gives us an additional method for losing mass in addition to tidal disruption. And kind of built into this bullet point here is the fact that now we can form cores or we can have this gravothermal collapse process. So we're really kind of altering the internal density distribution of the satellites. Okay, so in the remaining part of the talk, just a few slides, I want to talk about a variation on this, where now I'm going to make my self-interactions no longer elastic. So we're going to allow energy to be lost in those interactions. This becomes an interesting counterexample, because now what we can start doing is allowing for our dark matter halos to continue collapsing further, because you have cooling mechanisms that can drive that. So just to kind of set up the problem, recall that when we talk about just non-dissipative dark, so regular cold dark matter, you would start off with the halo collapsing. That comes from just the virial theorem. When I have 2k plus w, when that's negative, my moment of inertia decreases. So I'm making my halo smaller, it's collapsing. And that ends up occurring up until the point where I virialize. And then I get a balance of forces, radiation pressure, so just a pressure pushing out and gravitational force coming in, and that stabilizes my dark matter halo. It just sits there. Now, if I add dissipation to the theory, what I'm allowing for is further collapse to occur. I don't end up hitting that virialization point. And so now my halo can end up collapsing to really interesting kinds of substructures. It could be a dense clump. Maybe it's something like a rotating disk, because effectively this is going to be very similar to like a gas, like what we're used to with baryonic gas, where we know that the gas collapses and forms a rotating disk. It can end up being kind of similar, where you end up forming a dark matter disk. Now, we know that all of the dark matter can't do this, because if we lost all of our halos, that would be bad. But we could potentially have a subcomponent of the dark matter that's allowed to do this. So we would have something that's more cold dark matter plus this dissipative component, and that could potentially still be consistent with observations. So as a concrete example of this, and to kind of start off building our intuition for this, we've been thinking about a scenario which is referred to as atomic dark matter, where we add essentially a copy of a proton, a copy of an electron, and a copy of a photon. That's all in the dark sector. So this is my dark proton, dark electron, dark photon, and it can form dark hydrogen. And that dark hydrogen can cool through emission of the photons. And there's a variety of different cooling processes that can take place. And the manner in which it will cool will end up determining the kinds of structures that you can end up forming. So to put this in perspective, let's just start by talking about how baryons cool, regular baryonic gas. And I'm going to show this by showing the cooling rate on the y-axis and the temperature of the system on the x-axis. And this is the standard plot for baryons. It has this very specific kind of structure that's set by which radiation processes are dominating at what temperature. To kind of walk you through the highlights, this peak down here comes from collisional excitation of hydrogen. So I bump my hydrogen atom with an electron, I excite it, and then the electron de-excites and emits a photon. This second peak here comes from doing the same thing, but with helium. And then up here at these very high temperatures, my gas is completely ionized. And so the prominent mechanism for cooling comes from bremsstrahlung, just illustrated there. So as the system moves to lower temperatures, each of these different processes will dominate, and that's what sets the rate of cooling. In an atomic dark matter scenario, so now I'm going to move over and say, okay, now I have a gas of atomic dark matter. If I set the parameters of that atomic dark matter to be very similar to the standard model, the cooling curve looks like the red. So very similar. In this region here, you're dominated by collisional excitation of your dark hydrogen. In this region here, you get bremsstrahlung of your dark electron off of your dark proton. You can see, though, you don't get that peak. And that's because we're working in a really simple model where we don't have helium. So that's gone. There's other things that we don't have here, like we don't have any molecules. If you had molecules, that would end up adding additional cooling pieces. Like you can increase the cooling rate here and also increase the cooling rate there. We don't have any molecules. We don't have any helium. We just have hydrogen. So this is what it looks like. So you can think of the x-axis here as being a proxy for your halo mass. As you decrease the size of the halo in the system, the amount of cooling changes. And then when you're down here, for really small masses, then the cooling just shuts off. Yeah, Kara?
Yeah, is there a reason why the dark matter peak is just slightly offset from the baryon peak?
Yes. So partly it's because the equations that we're using to model the collisional excitation of the dark hydrogen, there's some factors out in front that we're sort of setting to unity and aren't completely aren't tuned to be exactly the same as in the standard model one. So that's probably what's giving that little shift there. Yeah. So if I go in and I now change my parameters in my my dark matter theory, so if I change the electron mass or if I change the coupling strength, what I do is I end up shifting these curves around, I increase. So you could just sort of intuitively realize, right, if the cooling is what's sort of setting the minimum size of my system, the rate at which it collapses, it's going to be very sensitive to the parameters that are going into that dark matter model. What's the net result of all of this? Well, this is nice for painting an intuitive picture for what happens, but to really be able to make concrete predictions, at the end of the day, we need to run simulations on this. And so that's what we've been working on. We've work led by my student Sandeep Roy. Sandeep has been going into Gizmo and modifying it so that we can include this atomic dark matter component. This is still work in progress, but I thought I'd sort of end by just kind of highlighting some very preliminary results that Sandeep found, and then I'll close out. So what Sandeep has done is he's now modified Gizmo so we can run it with two different dark matter models. So we can have cold dark matter, and we also add atomic dark matter to it. The other part, probably admittedly the harder part, is the atomic dark matter piece that he's added now can cool. So all of that cooling physics has to be implemented properly into the code. All of that's been done, and we've started running cosmological zoom-in simulations, sort of testing it and making sure that everything's working properly. And Sandeep is sort of right at the stage of starting to do some high-resolution runs with this. And so I'll just show you a few movies before ending, just to kind of illustrate the differences that you get when you make all of these assumptions. So here in this panel here, this is just the cold dark matter in our simulation, starting at redshift of around 4. I'm going to get it going. It's going to grow into a Milky Way sized halo. So here's the center. It's doing the usual thing you sort of expect from cold dark matter. You have these sort of smaller satellite galaxies that are falling in and they're merging. The central halo here is growing. Sort of standard stuff. I'll let this one continue running. And then on the right, I'm going to show the baryonic gas in the simulation. So you can start seeing, right, gas is much more complicated. It's shock heating. It gets shock heated. It's collapsing. It's forming here at the central disk in the galaxy. You see this is a satellite coming in with its own gas and sort of gets accreted onto the main disk here. And this just keeps going, right? So here we're almost at present day. Now you can really sort of see the central part of the dark matter halo, and the satellite mergers are continuing. And then here with the baryonic gas, we're almost at Z equals 0, and we have a stable disk that's staying there and continuing to rotate around. I'll let this run to Z of 0, and then I'll show you what ends up happening when for the atomic dark matter in the simulation. It's like almost there. Yeah, there it is. So just sitting there, rotating, doing its thing. Okay, so this is in the same simulation. This is what's happening to the atomic dark matter gas. I started at showing you here starting at redshift of 4. Here's the center of my Milky Way, and you can already see something unusual, right? This is dark matter. It's a little disk right in there. Okay, Now, I'm going to set this going so you can see how that dark matter disk evolves. So here it is, it's sort of churning away. Every time there's a new satellite that falls in, you see that it has, like, it oftentimes comes in with its own little rotating dark matter disk in the center that accretes onto the main one. So here we're at like redshift of 1.5, and we have a nice little robust rotating dark matter disk that's in the center. Here we go. This is where it starts getting weird though. It vanishes, goes away, goes away, goes away, it's gone. And that's around redshift of 0.8. So I'll just let that continue, but it pretty much is just going to end up looking like that for the rest. So this is all coming from the fact that the cooling physics is different between our dark matter model and our baryonic model in the and also the fact that we no longer have feedback. We do not have any feedback. So what's happening here is that as the atomic dark matter gases collapse to form a disk, that disk is rotating, but it's going to continue to fragment and continue. The gas is going to continue collapsing. And there's no additional baryonic feedback in this. No additional feedback because we don't have any stars, we don't have any supernova, we don't have any dark supernova exploding or anything like that. So it just that rotating dark matter disk ends up fragmenting away into dark clumps that you don't see in the simulation, that you don't see in this particular movie. But the rotating disk part of it just kind of vanishes. So we're sort of very much at the initial stages of this, but what we don't yet understand is sort of, and is on the long list of things to kind of study, is what ends up happening to all the dark matter fragments that end up forming. They're probably like flying around. They're probably doing something very bad to the galaxy, right? And are there ways in which we can actually use that to go out and search for these kinds of things and exclude these types of scenarios? Also, this will be very dependent on the parameters of the dark matter model, right? Because that's going to set the cooling physics, and that'll change whether or not that disk forms or doesn't form, or exactly what's happening there. So much work yet still to do, but sort of we have an indication that this is sort of working and is leading to some intriguing results to dig into. And this is the final time I'll show this, which is just our accumulating list of ways in which changing that dark matter model ends up changing the galactic evolution. Now we've sort of added how it ends up affecting halo cooling and potential fragmentation of the halo into dark substructures. And so with that, I'll just conclude. So I hope I've been able to kind of show you the wealth of interesting physics that could come about when we think about the impact of dark sectors on galaxies, and also on scales that are smaller than the size of galaxies. For the concreteness in this talk, I just focused on two examples, so elastic self-interactions and dissipative self-interactions. And I think just between those two examples, you can sort of see that there's just a whole variety of ways in which those the fundamental parameters of the dark matter model end up impacting things like populations of satellite galaxies, the individual properties of satellites, and so on. This is part of a long-term effort to really be able to go from a wide breadth of dark sector models to predictions using simulations to clear roadblock maps for what to do with observations. So by taking those simulations, turning them into mock catalogs, and then using that to think about how that ends up impacting how we should be interpreting results from upcoming surveys. So still a lot of work to do heading in that direction, but I think we've sort of been building up a lot of intuition for understanding like how to approach the problem. So I'll end there, and I'm happy to take any questions.
Okay, that works. Can you go back to the one slide that showed the elastic self-interacting dark matter and how the profile changes based on the baryonic feedback?
This one?
It's a little bit.
This one?
This one, yeah.
Yeah.
So you said sort of as a rule of thumb, self-interacting dark matter sort of leads to this coring, but it actually looks like once you add the baryons, it actually makes the cusping steeper towards the center than CDM. Mm-hmm. So it looks like it sort of has the opposite effect. And I was just curious if there's sort of an intuitive way to understand that.
Oh, so, well, the fact that it turns cuspy is because in this particular example, they've added enough baryons to the system that they've deepened the gravitational potential well to such a degree that it can no longer core. The dark matter no longer can move out. It's sort of stuck in the center. So, and the degree to which that happens is going to be sensitive to just how massive the disk is you add. So I don't remember the details of exactly what they did. So, but that'll set just how cuspy it's getting here. Yeah, I don't know. I mean, you can sort of also see that, sort of similar kind of behavior that's occurring here. This in the cold dark matter is probably coming from like adiabatic contraction when you add the disk in.
Sure.
Yeah.
And then I had another question.
Yeah.
How does the gravithermal collapse profile sort of differ from, say, just a really cuspy profile? Because you have like a really tight core, right?
Well, actually, Oren can answer that. He has some plots, so his computer can answer that in some detail. It'll end up looking something like this.
Okay.
Yeah, so there's sort of like a flat core in the middle part that sort of rises with time, and that's the actual collapsing of the core. Yeah.
Big difference is the power law that you get at the center.
Yeah.
So if an NFW belongs to -1, you'll get a much steep power law and some radius, which is the core radius to change. Thanks.
Yes, that was very educational. You didn't say anything about gamma rays. I was wondering whether the in their viable parameter space within become velocity dependent, there are any predictions for gamma ray fluxes that you might produce in the annihilation self-interacting.
Oh yeah, yeah. So I just didn't have enough time to talk about, but yeah, if you have so if you allow the dark matter if the dark matter can annihilate, it doesn't necessarily have to self-interact in order to be able to produce cosmic rays, but so long as it can annihilate into the standard model, actually the same mechanism that gives you that will like set the relic abundance here, like the same kind of interactions that would set the relic abundance just in the WIMP scenario, like if you have these kinds of dark matter annihilations, that's the same thing that would be happening in the center of galaxies that would give you gamma rays or cosmic rays or anything like that. Yeah, and there's a whole host of searches for that, so that would be.
Yeah, but my question was whether, in your particular model, whether there are specific regions in your viable parameter space where there are sweet spots for such annihilation signatures.
Oh, in the SIDM parameter space?
Yeah.
It'll depend. It'll be highly model dependent. So what I showed here when making these constraints, here, these constraints, this was trying to be very agnostic about whether or not the dark matter was interacting with the standard model. So in some sense, these are the most generic constraints that you could place on the dark matter if it's self-interacting. But you can then, even though it's self-interacting, also then add a way for it to talk to the standard model, and that could potentially end up giving you gamma rays. Where you would end up having exclusion in this space would be highly dependent on exactly how you make the two talk to each other, the standard model and the self-interaction. So it's a little difficult to be able to sort of say generically where it would fall because it would be really model dependent.
Actually, I had a question about you had a plot with the feedback showing the inner slope of the dark matter halos in the very beginning.
Yeah.
So it seemed like the low mass ones had a slope that was steeper than that of NFW. So I was wondering if that was resolved, and yeah, because it may be degenerate with some of the other gravithermally collapsed or resistively cool cores.
Yeah, that's a good point. It's a bit artificial because this is coming from reading off the inner slope at about 1% at a distance of 1% of the virial radius. So this is just the way it's read off in the simulations. So that's like saying I'm like reading it off like here, but not quite here. So I think it's just coming from that. Yeah. Yeah, but that was a good point. I meant to highlight that and then I forgot.
Any other questions from the room or Zoom?
The dark photons. So I'm not very familiar with this, but I can imagine that maybe at very high receive, you are producing many of these because I don't know, the density is very high. So will these dark photons somehow behave like normal photons and will change maybe the expansion history of the universe, or?
So are you're talking specifically in the context of this ADM model, this atomic dark matter model?
Yes, exactly.
Yeah, okay. Yes, it does end up having, I'm just trying to flip to it. This will end up having cosmological implications. And actually there's a group, David Curtin and his student are actually working out which regions of the parameter space are consistent with cosmological bounds. It ends up affecting like baryon acoustic oscillations in the early universe. And so there's a sort of famous paper by Francis Yassin where they work this out, but with some specific assumptions. So David Curtin is trying to update those now. So in Francis's paper, they said that it sort of ended up, their claim was that atomic dark matter could only be about 5% of all of the dark matter, but it's subject to a set of assumptions. And so releasing those assumptions actually means that it could be a higher fraction. And so that's something that's currently being worked out. But yeah, it's actually a very important part of the story. Yeah.